Hello. Hello. Hi, welcome to the seventh live session of Concept Topology 1 course. So from today onwards, first we shall go with we shall try to look into some assignments that's already been released. And then if it time permits, then we'll go to for learning some new chapters. Okay. But for the time being, from today, we will start with assignments. Uh, so, let's we shall walk into backwards. So first we shall start with assignment. One. Yeah. So let's start with let's start with sixth assignment. Okay. So first we'll look into objective, and then slowly we'll look at the subjective assignments. Okay. So this is assignment. So the first question is the following. Suppose if x and y are spaces with a subset of x, b subset of y. These are from two first questions. The boundary of a cross b is equal to boundary of a cross boundary of b. Is it true or false? So, how to adapt, at least how to guess that this problem, this may be true. How to guess? So, so the technique is the following. So, we have a cross b, its boundary is by definition this is a cross b closure minus a cross b interior. Closure means what? Closure means a closure cross b closure minus a cross b interior. So of course this thing cannot be written as a closure minus a interior cross b closure minus b interior. So that's why it is not possible. Generally, at least common sense says that this is not equal in many cases. Um, so this is the one possible way that we can check this given example is true or false. Okay, but in order to prove that in order to so we need to provide a counter example at least, right? The counter example is as follows. So take x equal to r is equal to y and take a is equal to b is equal to 0 1. Then boundary of a cross b, this thing is what? The boundary of a is what? 0 1 cross 0 1 means it's just the unit square. Okay, then its boundary will be what? Its boundary will be just the border. Basically the border of the unit square. Just what? This is yeah, 0 cross 0 1. Sorry, this is equal to what? This is equal to double down 0, comma 1 cross close 0, 1 union, because this portion, this portion, you need to put this portion or this portion. So this is 0, 1 cross 0, comma 1. So of course this is not equal to del A cross del B, right? So that's why it is not equal. But anyway, the correct adjustment is the following: del of A cross B is equal to del A cross B union E cross. This is the correct statement. Okay, you can try to prove, and if you can't solve it, you can ask me in the next live session. Okay, so this is the correct statement. Wait a minute. So let me. So the next problem is the following. So let xi be a family of spaces. Then the box topology on x equal to product over xi is finer than the product topology on x. So what does this mean? So I mean, since it's the infinite product space, so as you may can remember that there are two different type product topology. So I mean, two different type of topology you can define. One can give the box topology, and another one can give usual product topology. But as you may know that um, but in general, box topology is bigger than, I mean, the finite and the product topology. Okay. So you must have seen in some situation those are equal, but that is not our concern. Our concern is that whether in this question this will be equal not or not. Okay. So yeah, so that's why it's an interesting problem. And by the way, it's a counter product, so we should write I belongs to n. Means it's not the counter product. Okay. So 1 minute. Hmm. So okay. So let's. So what is the characterization of the product topology, or how we can characterize product box topology? So basically, the product topology on X is the smallest topology such that each projection map PJs contains. So product topology on X is smallest topology such that the projection map contains. So this is the characterization. So in the product topology, those these Pj inverse Uj open in Xj, these things are open in Xj as its subbasis. Okay. Now because so obviously one can write Pj inverse Uj is equal to product over Wi. I belongs to N. For Wi, we can write this as W as I if I not equal to J, Uj if I is equal to J. So this P inverse, so these things are open in X with box topology. So each of these P inverse Uj's, P inverse is Uj's open in box topology. So uh, since by P inverse in the subbasis, right? And subbasis for the product topology, and each of these are open box topology. So the whole product topology is equal to the total box topology. Okay, so these are. So let's take the next question. So the next question. What? So the next question is the following. Uh, so we have a function. Sorry. So what is happening? So this is f R2 0 infinity. It is a function defined by x goes to x square. This map is quotient. True or false? So how to check the sum map with the quotient? First, we need what is the definition? So the definition is as follows. So for portion order, we need to check the map is continuous, subjective, and I mean, if the map is from P X to Y, then P inverse C is open if and only if it is open in Y. It's if and only criteria. So first we will check this map is continuous or adjacent. Of course, this map is continuous plus adjacent. So let if inverse U open in R. So we somehow need to show that U open in 0 infinity. So what is the map? So let's take a look at the graph of this map. So we are taking a F inverse. So we are taking some U here, and we are considering its inverse. Sorry, what is the U? Yeah, okay, yeah. Sorry. So we are taking some U here, and we are considering its inverse images. Okay. So this part, and then in the here projection. Okay. So obviously this is an open because I mean these portions are open portions, right? Since here this is an open portion, this is an open portion, so only open portions will come. So that's why, at least intuitively, so of course, so intuitively F inverse U has to be open. Sorry, U has to be open in 0. But now, how to prove it? So for proving this, we might need to use some technique or trick. So well, let me think. So, so what are the possible ways to do that? So suppose, so let A belongs to A. Okay. Sorry, not A. Suppose if A is equal to U, then we can find a delta such that minus delta plus delta sum of it. And this implies that A belongs to 0, delta is such. Okay. and if a non-zero, then I mean, so of course, so root a non-zero, I mean, anyway, root doesn't make sense anyway, so it belongs to a inverse view. So we can find an R such that 0 less than R less than root a, such that root a minus R to root a plus R solve of a inverse view. And so A belongs to a minus R whole square comma root a plus R whole square. This observe here. Hence, U is open. Okay, so I mean this is the proof, but honestly speaking, this is the MCQ type question. So I mean anyway, I mean you can guess what is the possibility and why it should be. That's why there is no point of putting this. You can give this proof, but anyway, this proof is good to know that some obvious things can be. I mean, some obvious things is not sometimes uh, easy. Right. So wait. So this is the way. So in the solution manual provided some alternate solution. That's also fine. But anyway, yeah, that's good. There is a good solution. So let me check the next question. Wait a minute. So yeah. So the next question is the following. So consider the unit circle S1 and put y is equal to 1 by n belongs both on the shelled for. So basically, so you, I mean, so of course, minor says so here doesn't matter product of same, but anyway, so you need to show that product. This means what? You need to check that singleton sets are closed or singletons are open. Somehow you have to do this. Okay. So how to? I mean, we need to check this true or false. So what are the possible ways? So, well, so I mean, of course, this should be false because none of the spaces are discrete. Okay, and since the product use the finite space, so box topology product topology is same. So if it is discrete, so each singleton set should be open. So that is not the case. So anyway, it is false. So one possible argument so is given that singleton 0 1 is not open as one. So 0 1 comma 1, which is nothing but 0 1 plus 1, not open as 2 plus 1. Okay. So that's why, but anyway, I mean, since if it is protocol is open to the form, so since obviously all this can't be open, so it is a false argument. Okay. So friends, so question before, yeah. So let x be the giving a set having so two element and let if x is a map defined by x a x q and b if x is smaller. So so the question is that then the quotient topology on x which is induced by its map here true or false. So what the question is? The question is that we have already given so some description if is a map from R to S is a map. So on capital X we have a topology. This is what this means. So the what is the topology that you q subset of X open can only that if inverse x. So this is the induced torsion. By what do you mean the induced torsion? Okay, so kindly wait a minute. I should back to this. So yeah, wait a minute. Wait a minute. Uh, oh, কতক্ষণ ধরে? এটা জোরে ধাক্কাবেন নাহলে শুনতে পাই। আপনি তো আস্তে আস্তে যে আমি শোনাই যায় না। অনলাইন ক্লাস করছিলাম। এখন কিছু বলবেন না, 9টার পরে আমি জিজ্ঞাসা করবো, ঠিক আছে? আর গেটে লাগিয়ে দিন। ওষুধ পাওয়া গেছে? ওষুধ পাওয়া গেছে? মানে স্প্রে না? দিয়ে দেখো তো কাজ করে কিনা। Hmm. So, okay. So what do you need to now? Okay, so this we need to check this map as in discrete or whatever. So let's take the all possible inverses. So if inverse singleton A is of course Q, and if inverse singleton B is R minus Q, and these are not open in R. So only sets open or closed in X are X and phi. So it is indiscrete. So it is indiscrete. That's okay. So this is one possibility. Yeah, one good argument, I guess. So basically, we need to check the inverse images of all possible subsets of X. I mean, then after calculating this thing, then you can check that this is indiscrete or what. Okay. So so in this way, this can be done. Well done. So let's get to the next problem. So the question is follows. Say let x equal to r, y is equal to double dot 1, 2, the Chbosky space with, whose open sets y, comma, 1, comma, 5. Then for each x belongs to R, let fx be the map given by 2 and 1 for all t not equal to x. So now question is then the topology on x induced by this fx x is the cofinite topology. Okay. So if so basically we have some x, we have some y, one with double no one with space opens up y one. So for each x belongs to f, we need so let fx with a map given by f equal to f. So the topology on x induced by fx is the cofinite topology. This is what. So how to do? So the same thing we need to calculate, right? What do you need to do? Mm, okay. Now, so since y is a space, so uh, this one is a sub basis for y. So the family R minus singleton x belongs to R is a sub base for the induced topology on R. And so this topology is cofinite topology. So yeah, so this is what. So let me wait a minute. So basically, also what I've done, since double term one is subbasis for y, so I'm sorry, singleton or subbasis becomes first space. The r minus singleton x or x values over r is a subbase for the induced topology in R. And so of course, it is the copart. Now, question number three. Let x tau be any topological space, and for each x belongs to x, delta x singleton x to x with an inclusion, then the topology on y, sorry x, induced by the family eta x. So how to do the same way? So we need to check the inverse image, right? So of course, it's a true function by how. So yeah. So I mean, look. So since singleton x are open in x, so I mean open in itself. So they are open in it, which tells that this topology induced by this eta x is great. So we have the eta x or the inclusion map. So basically, whatever singleton is open in itself, so they are open in capital X also. So this tells that this collection eta x is discrete. Okay. Okay. So I shall back. So, going to the next question now. So, these are subjective questions. Okay. So, we have x equal to R2 and we are defining and this as. So, this is a relation we are defining and let x star be the corresponding quotient space and determine uh, family space Y homeomorphic with x star. So, what are the possible ways this problem can? So, basis of first observe that what is happening in this question. So, we have basically R2 and we have some equivalence relation defined in this. Now, so how does this equivalence relation look? This relation looks like the following: x1 plus y square, sorry, x2 plus y square. So, well, so so basically, what is it? So, so what is the curve of x plus y square? So these things looks like the following, right? Now, as per this thing is telling, uh, we are taking all these points of this particular parabola to a single point. So, so in this way, we may it's possibility that after taking the quotient, we end up with having only this line. So, possibly we somehow need to show that quotient space is homeomorphic with the real line. Okay, somehow this is, I mean, this is my possible guess that this is sorry. So possibly this is what we need to show. Okay, but how to do it? So it's a very big question. So let me so um, Let me check it out. Yeah, got it. So, correct. Okay. So, so how to do it? So somehow we need to. So this is our space. Okay, and we need to figure out some map fx to r, which will be quotient and fx is equal to fy if and only x is equivalent to y. Somehow we need to figure out a function. So that such a thing happens. Okay. So one possible way of doing this. So so it's a very natural choice to get a functioning gap defined by a of x comma y is equal to x plus y. So at least two elements, 2 points go to same if and all equivalent. That is if they lie the same half, right? So firstly check that this map is continuous. It is obvious, right? So in order to checking this question, we need to check that this map satisfies the certain property. Okay, but there is a slight trick. It is not always possible to check that some given map is always rejective, always that satisfies the question directly. So for that, so there is a basic techniques that are following. Suppose you have a map P y such that there exists a map in the reverse direction. Y such that P compose F is the identity of the codomain. Then this will tell that P is a quotient. Okay. So so in this case, if we take up define map G from R to X defined by Y equals to Y, then sorry Y equals to Y comma 0, then obviously if compose G is equal to identity map for R. So this implies what? F is a quotient map. Okay. So yeah. So the quotient space is the quotient space X star is homomorphic with R. Of course, nevertheless, this usual topology. Okay. So this is yeah. So this is very, so I mean so one good question is to ask that. One. So the technique goes as follows. So yeah, so I mean, so basically, someone need to figure out that if with respect to some, I mean, so two things that equal to life in somehow we need to figure out that which node thing it is. So it is purely hook and crook. There is no okay. So yeah, okay. So so the next question. So let I is equal to third bracket close to 1 and x is equal to product over I product college. That is this thing is for I to the power and say this to hold it down. And defining a to the psi q I square psi q x is equal to 1 if x q equal to 0 if x not equal to q. So so now we need to show that the self-based topology on a tau restricted twist spreads. So basically, we need to check that all singletons capital here of penny. This is what we check some. Mm. So yeah. So choose q belongs to I with q equivalent I. So 0 does not belong to q. And let u is equal to product over I. Why be such that u is equal to I. Q I not equal to q and q p was equal to q. So of course then u is open in x, and so u intersection a is open. But of course, since u intersection a is equal to all those a from I to I, thus that a belongs to u and b to a, this is equal to a from I to y. Thus that if equal to tau q, tau p for p belongs to y, and if I belongs to I for all I belongs to. So this is what. So this implies that if p not equal to q, so this implies if q is equal to tau pq, which is equal to 0, which so that thing, so the gx does not belongs to uq. This implies that f does not belongs to intersection f. So therefore f equal to is iq, and so u intersection a is equal to, so iq is open. Okay. So this is the, so yeah. So this is the, so yeah. So this is the total assignment. Okay. So there was in between a question which I have skipped because I don't think right now this question does any sense. So we will get back to this question after at the end of the course, because right now it has nothing to do with our concept. Okay, that I personally use. Okay, so let's move into now assignment one. Wait a minute. I should have back. So let's start asking the part. So the first question the following. Suppose consider R2 and here consider the state of all straight line as a subbasis. Then the topology generated by it is the discrete topology. So it's of course true false question how to do it. So yeah. So so what? Wait. So this following question. So look. So we have R2 and we have some more straight lines. So the straight almost straight line subbasis is what? So what are so I mean so 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 since subbase we have subbasis. So what are the basis? The basis elements the intersection of so basis is what? Basis can be written as intersection of so finite intersection of subbasis, right? Finite intersection of subbasis, right? So so we have some instrument here. Here also we have some instrument. So this is the point of intersection. So so each of this single this means what? Each of the singular points is open in R2 with this topology tau. So this means what? This becomes a discrete topology. Okay. So here we only have used the fact that so here we have only used the fact that basis elements is finite intersection of base elements. So that each single point is coming to the open. So that is so that's why so this is a discrete topology. Okay. So go to the next question now. With Hmm. So, okay. So, so next question is the following. Let capital B1 be a basis, the topology tower on X, and capital B2 is the basis for a topology tower on X. And if tau 1 substitute tau 2, this implies beta 1 substitute beta 2. So this is true or false? So, I mean, look. So what the usual, I mean, logically, look, if tau 1 substitute tau 2 means what? Every open set is tau 1 is also open in tau 2. So if we take a best element of tau 1, that is also open in tau 2 means what? That, so a beta 1 is open in tau 2 means what? That beta 1 will contain beta 2. So this should give beta 2 subset of beta 1. So that's why it should be false. So now we need to figure out the uh, exact solution or exact counter. Okay. So for counterizable, choose X to be ABC discrete topology with beta 1 to be this A, singleton B, singleton C, doubleton AB, singleton A, singleton B, singleton C, doubleton BC. These are both bases of discrete topology. So, so I mean, so obviously both are bases, but the topology is tower here to tower. So here for tau 1 and tau 2 because both are discrete topology, but of course no one is a subset. So that is why beta 1 is not beta 2 and beta 2 is not a subset of beta 1. So that is a false. Okay. Going to the next question. So yeah. So um, the next question is follows. Let f x star one two sorry y tier two be a continuous function. And if beta is a basis for tau two, then f inverse PV beta is necessarily basis of tau one. So basically, what is the question? This question is that suppose we have some collection of bases. So its inverse will be basis of the other the domain. This is what we need to show. So so first let's think about what are the I mean is it possible or not? Okay, so this is first step we need to carry. You carry on. Let me. I need to check some solution here. I mean, I need to check whether this solution, what is the solution given there. I mean, so if possible, then I can provide a better solution. So wait a minute. Oh, so so basically, what so we need to somehow check that this inverse image of basement or the base element basis on. Okay, so what are the possible ways of doing that? Let me down it here so that I can write properly. So, okay, so we have only I mean, look. So in content, we have seen that inverse image of open is open. Okay, but of course, inverse image of base element is not necessarily basis element of the domain because if such a thing happened, then it would be a theorem, right? I mean, it is a very nice thing to have. So of course, such a thing is not possible. So we need to somehow find a counter example of that. So so take tau to be a discrete topology. And let U is the usual topology. The identity map from tau to RU continuous. And so we have beta is equal to open a basis for U, but it is not a basis of tau. So what we took, uh, so uh, so tau is a discrete topology we took, and we took the identity map from R tau to RU. So use the usual topology. So beta is open with base element view, but whatever one inverse open AB. So open AB, but this collection open AB is not a basis for R with usual topology because R discrete topology because R discrete topology has a basis of singleton of all possible singletons. So the collection open AB where AB belongs to R can't be a basis for the discrete topology. That's why it's false. Okay. So this is a proper counter example. So let's move on to the next example. Wait a minute. Hmm. So 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 choose any I which is natural. So this is the question as follows, and we have xi to be r with. Oh wait a minute, let me check if it is one or not. Yeah. So x equal to r with usual topology, and let the x equal to product over xi and belongs to n equipped with box topology tau. Let ai 1 by n belongs to n for all I, and let a is equal to product over ai. Then the question is then the subspace topology tau restricted to S. So it is true or false. So how to do? Let me check the solution here. Let me think whether it is possible to get some new solution other than this. So wait a minute. No, okay. So let's discover the solution is given in the manual. Okay. So the solution goes as follows. Since each AI is discrete, so for each I belongs to I, the collection beta I from 1 by n belongs to n is a base for each AI. And by definition of box topology, beta product over bi, bi is the basis for the box topology. Wait. So, wait. Oh, so okay. So since this beta product beta I is basis for the box topology. So I mean since the singletons, this belongs to B. So the box topology is great. So this is the argument. So since each AI is discrete, so for each I, this collection beta I 1 by n is base for each I. So by definition, box topology, beta product over beta I is a basis for box topology. So since the singleton belongs to capital B, so box topology is discrete. So this is the argument. Okay. So let's go to the next question. So let's take the next question. Solve it or not. Oh, so the next question follows. Suppose A, B are two disjoint subsets of X tau, such that X is equal to A B, and subspaces and so tau restricted to A and tau restricted to B are then tau is then necessarily. So we have to disjoint subspaces. So the X gradient and B, and so their restriction are discrete. So we need to check that the whole topology is discrete or not. Okay. So now tell me how to check this. Okay. I should back some notes. Yeah. So okay. So we need to somehow check that the discrete set is true or false. Okay. So I mean, so of course it's false, right? I mean, somehow it is obviously false because I mean restrictions may be discrete because restriction may contain even single limit, right? So, but anyways, we need to come up with a concrete example. So, like, so one example may go as follows. That wait a minute. So yeah, so the example goes as follows. So take X is a two-point space with since we have considered two-point space with Kronecker topology, we'll consider and tau is equal to the singularity. And if we take capital A to be singleton A and capital B to be singleton B, then the south space topology is then on A and on B are discrete. Okay. But of course, as a whole, the given topology is not discrete. Okay. Is now given topology is not discrete. So that's why. So this. So now, so of course, this type of solutions are actually tricky solutions. There is no hook and crook method. There is no straightforward two times. So you need to practice more and more in order to get these things. Guess it's easy. Okay, so that's so yeah. Okay, so let's go to the question. So the next is the follows. Mm, So, so next goes as follows. So the question is namely, so if beta is equal to all squares centered at origin, then the topology on R2 having beta as a basis is the usual topology. So so basically, what I take beta to be all the squares in the origin, centered at origin. So this is all possible. So this is basically the concentric square center origin. So this forms the basis of topology. I mean, of course, it's not because um so so if you take any point, so there is a square containing the point. So that's okay, but What about two squares? Suppose we have these two squares, then their intersection is not necessarily square, right? So that's why, so that's why the second axiom is not satisfied. Okay. So now the next question. So the X tau is a topological space such that tau is coherent with any family of subspaces Xi that is when X equal to union Xi. Then tau has to be necessarily discrete. Okay. So basically, so tau the topology is coherent with house. Coherent is what? So basically, U subset of X open, that is coherent means what? Coherent means U subset of X open equal to intersection Xi open Xi for all I. So tau has to be in a discrete. How to prove it? So what are the possible ways to prove this? Wait Hmm. So So, so this is what, so now we need to check this to done or not. So, so the answer is will be true. So let's try to prove this. It is given to be true actually. So let's prove it. So since tau is coherent, so with any family, so take xi to be similar than I for all I. Tau is the coherent with the collection xi, I belongs to x. Okay. So since for each I is open in x, so this is what? So x discrete. Sorry, so x tau is discrete. Okay. So I mean, so see, singleton xi is open in capital X. So singleton I is open in capital I. So this is what singleton I is open. Singleton I is open in capital because singleton I intersection capital X I is equal to singleton I, and singleton I intersection capital X I is equal to empty for I not equal to J. So this is what singleton X I intersection singleton I intersection X I is open for all I. So that's why singleton I is open in capital X. This is what all singletons are open in X. That's why the topology X stars is great. Okay. So let's go to the next problem. Oh, so okay, so let's move to the general question. Hmm. Okay. So fix an integer n positive integer, okay, n belongs. And let x is finite. Show that the collection u sub of x as that x minus u is equal to n forms subbasis for the cofine topology. Alright. So basically, X infinite and we cast all users that the complement has exactly capital element, small and element. So this one's subbasis. So, so clearly collection is sub of complement. Okay. So this tau of f. Okay. So now it will check that this thing substitute tau. So we need to check that. So if we take some x belongs to x, and if we somehow show that its complement belongs to tau for all x belongs to x, then we are done. So what are we doing? So we choose to set a b with x such that the number of elements in both a and b is n minus 1. We add a intersection b is equal to a intersection singleton x is equal to b intersection singleton x is equal to jumping. So x minus singleton x equal to x minus a union singleton x union x minus b union singleton x, and so we are done. Okay. So this is one possible argument. So I shall also think about some new argument what is possible and not, okay? Because anyway, so we shall continue the next live session. Okay, so I'm stopping here. Please go through the videos with the lecture. If you have any doubt in understanding, please ask me in the next live session. Also, you can do an email to me. I will reply definitely. Okay. Thank you. I'm leaving the call.